Hey guys, I finally got around to integral videos, and I'm gonna start trying to guide you guys through integrals from in calculus AB and maybe even BC. So there are so many ways you can solve integrals. It's just crazy. It's not like differentiation. It's not like derivatives where it's just like straightforward. You just use whatever rule that you use like based on the situation, like the product rule, the power rule, um, the chain rule, etc. With integration, it's a lot more problem solving based. You need to like think more about your decisions, and it's a lot of fun. So like the methods I've heard of are the reverse power rule, the most basic one that you can use for polynomials and negative powers. There's also U substitution, the second most basic one, partial fraction, integration by parts, which I think is in calculus BC now, because my calculus teacher told me that everybody was very stressed out by that method. There was also another there's more calculus BC ones such as Weierstrass substitution. Actually, I'm not sure if that one's in BC, but there's also trigonometric substitution, hyperbolic substitution. That's a lot of substitutions. Complex analysis, and I think that's it for BC. And then there's a couple of scary ones I've watched. There was one where this guy integrated using matrices, and another one where he was integrating using contour, something like that. Yeah, those ones are scary. It gets scary when you combine calculus with linear algebra. But yeah, anyways, I don't think those are even in BC. So, anyways, yeah, I'm gonna try to guide you guys through the methods that are used for integration in AB and maybe even BC, like some of them, before the this current school year ends. So here's a couple of things before we begin. Just a couple of quick things I need to point out. Integrals, like all other operations, have names for their parts. Like say you have the integral of x squared dx, sure. Yeah, so you have that. So, like other operations, such as multiplication when you have 5 times 4 is equal to 20. 5 times 4 are the factors, and oh, I forgot to put the 0. My bad. And then for 2 plus 3 equals 5. The 2 and 3 are the addends, and so for integrals it also has like a name for its parts. So the sign here is just called the integral sign. Um, dx is just dx, and then x squared, the inside of the integral, the function part that you're trying to integrate, is called the integrand. 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 Now that one is kind of weird. I don't know if there's one for derivatives, but yeah, those are the parts. And also, integrals will always have a dx. It'll always have them. It's like how with derivatives, you're supposed to find dy dx, not just dy. You're supposed to find the derivative of y with respect to x. If you don't have anything to find the derivative with respect to, then you can't find it because you don't know what you're trying to find exactly. It's the same with integrals. If you want to find the integral of a function with respect to x, you'll need to have the dx there. Otherwise, you can't integrate it. So now that that's over with, let's start integrating. So our first example will be, let's say, the integral of x to the 6th dx. Sure. So there's something we need to know before we can do this. So in my last video, I explained that the integral for any general x to the n dx is going to end up equaling 1 over n plus 1 times x to the n plus 1 power plus c, where n is obviously the power, the degree, or not the degree, just the power of the term that has said x. So in other words, you just add 1 to the power, and then you divide by that new power. So in this case, you're going to take x to the 6th, you're going to add 1 to the power, that's going to equal 7, and you're going to divide by that new power. So you're going to get 1/7 x to the 7 power. And you're done. So now you can put the plus c. That one was pretty straightforward. So now for the next example, we'll integrate, let's say, we'll find the integral of 6x to the 5th, do a polynomial now, 6x to the 5th minus 2x cubed plus 21 dx. So now there's something else we need to know. An integral of a sum is the sum of integrals. In other words, the integral of f of x plus g of x, two functions of x, and dx, that's going to be the same as the integral of f of x dx plus the integral of g of x dx. So it's like derivatives where the derivative of f of x plus g of x of two functions of x, the derivative of this entire thing will be f prime of x plus g prime of x. The derivative of f of x plus the derivative of g of x. So in this case, so you could say the same thing here. So like this is the same as the integral of 6x to the 5th plus the integral of negative 2x cubed plus the integral of 21, all with dx's at the end. You always need the dx at the end of the integral. And so this will equal, let's do the first term. So what is the integral of 6x to the 5th? You add 1 to the power, 5 plus 1 is 6, and you divide by the new power. Since you have the 6 in front, and you're dividing by 6, there's going to be no more 6's. Actually, I'll show you. So you have 6 x to the 5th. You add 1 to the power, that's 6, and then you divide by that new power. Alright? So that's going to simplify to 6 over 6. Those will cancel out. You'll just be left with x to the 6th. And then you have the minus sign here. 2x cubed. So again, you add 1 to the power. That's going to be to equal 4 for the power. And you're going to divide by that new power. And so then you're going to get minus 2/4 just simplifies to 1/2 x to the 4th. And then plus, if you want to integrate a constant, all you need to do is just put the independent variable in front. It's just going to be 21x. And the reason for this is, let me just put it here, plus, technically when you have a constant, it's the same thing as having it multiplied by x to the 0, since anything to the 0 power is 1, right? You're going to add 1 to the power, that's going to equal just 1, and then you're going to divide by the new power, divided by 1. So anything divided by 1 is just itself, so 21 will stay the same, and x to the 0, or in other words 1, will now become x to the 1st, just x. So in other words, when you want to integrate a constant, just put x in front, or u, or whatever independent variable it's going to use for that problem. So now all I need to do is just simplify it. We already simplified it right here, and we're done. So we can just put a plus c. It's important that you put this plus c, by the way. You'll need the plus c for when you do indefinite integrals, or when you won't need the plus c when you do definite integrals, when you have limits of integration a and b, because then you'll know like where the function is. But like for the general function, you'll need the plus c. So that's it for the second example. So let me just clear this one out, and then we'll be on to our third problem. So let's get away from polynomials for a bit and let's finally start putting x in the denominator. Make it a little more complex. So we're now going to integrate negative 2 over x cubed. dx. So, what you need to do is you should try to get into the habit of like converting radicals and rationals into powers. It'll usually make the problem more solvable. So since we have x cubed in the denominator, we can just raise that up and make that power the opposite, right? That'll be, so that's going to be, oh, by the way, when you have a constant inside, like when you have an integrand, like when you have a constant in the integrand that you could factor out, you could factor it like completely out from the integral. You just like take the -2 all the way into the front. And again, it's like derivatives, how if you differentiate, let's just say when you differentiate ax to the n, where a is the coefficient and x to the n is obviously the function part, that's the same as taking the constant out and differentiating that function part, right? Obviously you're not able to take out the actual like x to the n. You're not able to take out the actual x to the n because the derivative of ax to the n is not equal to just ax to the n. In other words, this rule applies for integrals as well. You could just take out a constant and continue integrating. And so now you're taking -2 times the integral of 1 over x cubed, and so that's the same thing as saying -2 times the integral of x to the -3 power, right? And so we're going to, let's just take this down here now. So -2 times, so now we're going to evaluate this mini integral here, the x to the -3 dx. So we're going to take the x to the -3, and again, I made that a little too big. We're going to take the x to the -3, and again, we're going to apply the power rule again. So we're going to add 1 to the power, is going to be -2 now. And we're going to divide by that new power, so 1 over -2. And so you see you have a -2 and another -2 here. One's the numerator and one's the denominator, so you can cancel those two completely out. And you'll just be left with x to the -2 power, the -2nd, which is the same as 1 over x squared. And we are done. So now I can put the plus c again and box our answer. So now for the final one, there's going to be only just one more example. So this one is going to be kind of tricky. Let's integrate. This is going to look simple at first, but it's not really when you try to integrate it for your first time. Let's try to integrate 1 over x. Plain and simple. I'll give you a hint. Remember what the integral means. So now just give it a try. Ready to continue? Alright, so before I solve it, let me show you why the reverse power rule doesn't work here. So we can rewrite 1 over x, we can rewrite the integrand 1 over x as just x to the -1 power, right? And so again, when we integrate, we're going to take this inside part and we're going to add 1 to the power. That's going to be 0, and you're going to divide by that new power. Wait a minute. We have to divide by 0. Well, that's no good. So we can't use the reverse power rule for this because it's useless to have an undefined area formula. So I hinted earlier that you need to remember what the integral means. So remember, the integral is the same thing. The integral means it's an antiderivative, right? So you'll need to memorize your derivatives for this. What is 1 over x the derivative of? That's what the integral means, right? 1 over x is the derivative of what? What should be inside this parenthesis, right? These parentheses right here. Well, if you can remember, you should come up with the answer of ln x, right? So then this integral should be equal to ln x plus c. Well, this is only half right. We know that, let me just draw a mini plane here. We know that the function 1 over x is defined on both sides, on the negative and the positive side, right? In terms of domain. Um, well, if you take if you take ln x, its supposed antiderivative, it's only defined on the right side, on the positive side. Well, we can't use an antiderivative that only works on half of the function. So how can we fix this? 1 over x is defined for all real numbers for 0, so how can we make ln x, its antiderivative, have that same property? Well, it's an easy solution. Put an absolute value, just put an absolute value sign over it, so that this is also defined on the negative side. Because the argument will always be positive, and that'll just solve the problem completely. So now, so this is important. Even though the derivative of ln x is 1 over x, the antiderivative of 1 over x is actually going to be ln the absolute value of x, if you wanted to find it for all real numbers. So now this is our real answer. So yeah, you'll need to remember that, and there's some more that you'll need to remember, like the inverse trig functions. Like, you know how the derivative of arctangent x is 1 over 1 plus x squared? That means the integral of 1 over 1 plus x squared dx is going to be the arctangent of x, the inverse tangent of x, plus c. So you already have like some of these integrals memorized, because you just need to like take the derivatives you already remember and think of it the other way. So that's all I'm going to do for this video. In the next video, I'm going to try to do some more complex examples that we'll still use like the reverse power rule for those problems, but you'll need to do a little bit of extra work before you actually do the integration. So anyways, I hope you enjoyed this video. Let me know what you thought about it in the comments below. If you didn't like it, let me know, and let me know why, so that I could be careful next time. I'll see you next time.